I pointed out that under authentication and authorization, there are changes, continuous changes, and Grizzly changed yet again. Actually, we had a lot of trouble with the previous release, Fulsome, and we never quite solved it. Actually, and Grizzly switching to Grizzly was a great help to our group, which was integrating OpenStack into FutureGrid. So we think that OpenStack is going in a good direction, and we already have found Grizzly to be quite effective. All right, so if we look at Grizzly, I already pointed out that Grizzly has a new token format based on standard PKI functionality. This gives it better performance and allows offline token authentication by clients, and it allows one to support multi-tenant environments with groups and things like that, role-based access control. So these are important changes, which are not new to the field, but they're new to OpenStack, and they allow us to give people a more conventional security and authentication and authorization environment. So we have to be, all of this unfortunately requires work, and every time a new version comes out, we need to redo our security work. And I say we sometimes have great difficulties, like we did with OpenStack Fulsome. And currently, you have a separate OpenStack account and portal account, and we could consider federating that, and maybe that's what we'll do. I've already discussed federation with Exceed, and we have learned a lot from the grid about how to do this. And we have to remember that all sorts of resources, Exceed, EGI, Genie, Azure, Google, and AWS, it's not so clear that it is realistic to federate with all of those. And then more research is needed here. And you can either have virtual organizations with federated authorization and authentication, or you can have an individual user who has multiple logins managed by a single system. There are various commercial packages that support this. All right, now we come to discuss some of the key technologies underlying FutureGrid Rain and FutureGrid Cloud Mesh, which is how we generate images. Here, image means machine image, the actual operating system, which and that image becomes an appliance when you add the actual user functionality to the software. And appliances are what we really mean by images here. So we look at a life cycle of an image. We create and customize the image. You select what you want, your OS, whether you want a VM or not, what user software you need, and things like that. Then we need to create that image, capture it as a template, and store that template in an image repository. That's why it's called abstract image. It's not actually stored as bits and bytes. It's stored as an XML specification. Then we need to take that XML specification and realize it, and that realization is different for each environment. Nimbus, Eucalyptus, OpenStack, OpenNebula, Bare Metal, Amazon, Google, Azure. You realize that templated specification in different ways. Pretty similar, actually, in most cases, but they're different. So that's called registering the image with a particular IaaS, NAAS environment, and then we instantiate the images possibly as a virtual cluster. So that's the 4 steps. So here's the first 2 steps, which is the user decides what they want, the particular OS type, the system architecture, the software packages. Is not aimed at any particular infrastructure like Nimbus or Amazon, and the image is stored in abstract fashion in the repository. And at this stage here, we also check that the software is totally up to date, and we've installed all the particular patches that are needed. If we look at this picture here, we actually check to see if this image exists already. And we do this by getting a base image, and well, I should say, see if the base image exists already. And then that gives you the core thing you build on top, and then you install the software and update the image. You actually, although it doesn't quite say that here, you also, of course, check that the full image doesn't already exist in the repository. So the actual image generation is done using OpenNebula, and the various virtual machines could be built with various different operating systems. Here's a slide which is done in more detail in following slides. This particular slide was the one in the overview. Here we actually go into a little more detail. This points out that these original slides describe phases A and B, and also phase D. Here we have the timing for phase in A and B of generating an image. And you see uploading to the repository of the template, it takes almost no time. We see differences between operating systems here. CentOS takes much less time to create the base OS than Ubuntu. The other times are a little more similar, although booting the VM is also quicker for Ubuntu. Here we have comparison. That here these were single nodes. Here we have single cores. Here we have multiple images done, and again we see that CentOS is quicker than Ubuntu. Here we have the phase C, which is to take the image and take a particular deployment platform, which is Xcat and Moab for HPC, and it would be Eucalyptus, OpenStack, Nimbus, etc. for clouds. And here's the time it takes to take the XML specification of the image, develop the appropriate image for the particular environment, and then store it in the repository for that environment. So each environment has its own library where you actually access the bits and bytes you need to put on your machine to actually run it. And here's the actual final dynamic of provisioning. You take it from the repository and you bring it down and put it on the nodes that are going to be used. And we already pointed out, and we'll discuss in more detail, why HPC, the bare metal Xcat and Moab, is somewhat slower than the virtual machine. It's a rather trivial reason described here. So why is the bare metal slower? You might have thought it was quicker, and that's just because we avoid bare metal boot in clouds because we use an in-memory boot, and the HPC nodes have to do a bare metal boot on all the nodes. Notice the HPC time was more or less flat as a function as the number of machines. That's because it's dominated by the boot time, and that boot time is done concurrently and is therefore independent of the number of machines. And then we haven't gone to lots of nodes yet, and we will see what happens when we extend to more nodes with the Grizzly environment.